So we're recording now. Okay, welcome everyone. My name's Lauren Decker. I am a non-federal co-lead on the IARPIC data management team. Jonathan Blythe, who actually just gave his intro, was the person who got me into this job. So thanks to him. I'm also the Chief Science Officer and Oceanographer at the company Polarctic. And I live in Las Vegas, which sits on the ancestral, traditional, and contemporary homelands of the Nuwu, or the Southern Paiute people. The Interagency Arctic Research Policy Committee, IARPIC, is a federally led program to enhance research in the Arctic. And by bringing together more than just federal agencies, but also states, universities, private companies, Arctic communities, and individuals, and as we heard, several international groups, we're working to support a 5-year Arctic research plan to promote Arctic research. Today is being hosted by the Data Management Collaboration Team, where we promote the data management principles of FAIR, findable, accessible, interoperable, and reusable, and CARE, collective benefit, authority to control, responsibility, and ethics. This is a contemporary framework for data management that balances that technical data sharing with ethical and community-focused governance. To that end, we have today with us Darnell Melvin with the University of Las Vegas in Nevada. I met him briefly at a university library open house. If you have one in your area, go. They are totally amazing. And he was introducing this topic that I have asked him to speak about today on graph databases. I did not know that there was so much technological infrastructure behind what I originally thought was just a graph. And so I'm really excited to hear why and how a graph can be a database, and how these networks of data can prevent silos, what your definition of ontology is, and how graph databases and these approaches can support data integration and knowledge discovery and interdisciplinary research. So without further ado, Darnell Melvin, Special Collections and Archives Metadata Librarian at the UNLV.
Good morning, everybody. Thank you for having me. I'm really excited to be attending today's meeting, and I'm excited to share with you some of the possibilities for incorporating graph databases into research workflows and research data management strategies. I would like to note that some of my examples and some of the data models presented today may come from the galleries, libraries, archive, and museums community. However, the concepts and the technologies discussed are broadly applicable and can be adapted to virtually any research domain. By the end of the session, you'll have a basic understanding of how graph databases differ from traditional databases and how they can be constructed and how they can support complex research questions and data integration. I'm going to turn off my camera just so things don't start freezing when I start doing my demo. Okay. So before we talk about graph databases, I'd like to start with a challenge that many researchers are encountering regardless of the discipline. So imagine we're trying to answer this question. How has changing sea ice conditions affected Arctic ecosystems and communities over the past 30 years? At first glance, this appears to be like a climate science question. However, answering it requires information from many different domains, right? You might need satellite observations, environmental sensor data, climate models, biodiversity records, geographic information, as well as scholarly outputs and research project data, and maybe even community or indigenous knowledge. The challenge is that these resources are often stored in separate systems. One database may contain environmental observations, another the publications, another the geographic information, and so on. And Each of these systems was designed for a specific purpose and often used different identifiers, different metadata standards, and different terminology, right? So as a result, answering complex interdisciplinary questions frequently requires research to spend a significant time discovering, reconciling, and connecting information from multiple sources before they can even begin their analysis. So, for example, a researcher may want to connect a sea ice observation to a geographic region and a species affected in that region, the publications discussing the species, and the researcher who conducted those studies, right? The idea is not that traditional relational databases are ineffective. In fact, they're really extremely good for storing, organizing, and managing your data. The challenge is that they're not designed to primarily to represent the complex networks of relationships that may span multiple independent systems. And this is where graph databases and knowledge graphs become valuable. Rather than focusing primarily on tables and records, they focus on representing entities and the relationships between them, making it easier to connect information across domains and uncover patterns that might otherwise remain hidden. In the previous slide, we discussed the challenges of answering complex research questions when information is distributed across many independent systems. Now let's consider a different approach. What if the data was connected? Instead of treating environmental observations, geographic information, publication, the researchers, and the organizations as records in a separate database, we could represent them as part of a connected network. In this model, a sea ice observation could be linked to the geographic region. That region could be linked to the species that inhabit it. Those species could be connected to their publications and so on. And rather than manually assembling these connections, the relationships become part of the data itself. And as you can see in the graphic, we move from an isolated data silo towards a web of interconnected information, where every node represents an entity, such as a person, a place, a data set, a publication, or an organization. And every line represents a relationship between those two entities. And this network of connected forms the foundation of a graph database and a knowledge graph. By explicitly representing relationships, we could traverse and explore data in ways that are often difficult to achieve within traditional database structures. So the previous slide introduced the idea of moving from isolated data silos to a connected web of information. And linked data provides a practical approach for making this possible. Most of us are familiar with how the web connects documents through hyperlinks. For example, one web page can link to another web page, allowing us to navigate between related pieces of information. Linked data extends this idea beyond the documents and applies it to data itself. Instead of simply linking web pages together, we can link data sets, people, places, organizations, observations, and other entities while also describing how they're related. For example, a sea ice data set could be linked to the region. The region could be linked to the biodiversity observations, and those observations could be linked to publications discussing the findings, right? And the term linked data refers to a set of best practices for publishing and connecting structured data on the web. And these practices rely on several key technologies. The first one is the URI, or the Uniform Resource Identifier, and it provides a unique identifier for entities and concepts. Just as every web page has an address, every entity can have a unique identifier. The second one is HTTP, or the Hypertext Transfer Protocol, and that provides the standard mechanism for retrieving information and those entities across the web. And then third is the Resource Description Framework, or RDF. And this provides the graph-based data model for describing these entities and their relationships to one another. And together, these technologies enable data from different sources to be connected, shared, and understood in a consistent way, creating what is often referred to as a web of data. This slide highlights the shift from a web of documents to a web of data. On the left table, you will see the traditional model of the web, which is centered around documents and information resources. In this model, links connect documents, and the meanings of the content is primarily interpreted by humans. The data itself is often unstructured or loosely structured. On the right side column, we see the web of data, and here the focus shifts from documents to real world entities, such as people, places, events, and data sets. And instead of linking documents, we start to link things. The information is structured in a way that makes meaning explicit rather than implied, allowing both humans and machines to interpret and use the relationships between the data. In other words, the key shift is not about connecting more information, but about making the meaning of that information machine readable and interoperable across systems. And this shift is what enables linked data and provides the foundation for graph-based approaches like RDF. So RDF is the foundational standard developed by the World Wide Web Consortium for representing and exchanging data on the web. At its core, RDF provides a simple but powerful way to describe information as relationships between things. And rather than focusing on tables, records, or documents, RDF represents data as a graph of connected statements about resources such as people, places, events, and concepts, right? And each statement in RDF expresses a relationship between two resources, forming a network of interconnected data. To support this model, RDF relies on a few key components, right? As mentioned earlier, URIs are used to uniquely identify the resources so things can be consistently referenced across different systems. We have RDF itself used as the graph-based structure to represent how those resources are connected. And then we have ontologies and vocabularies, which provides the definition for the types of relationships and the entities being described, helping ensure that different data sets can be understood in a consistent way. And together, these elements allow data to be connected and interpreted across the system, forming the structural foundation for knowledge graphs. RDF represents information using simple statements called triples. And these triples form the basic building blocks of the semantic web and allows data to be expressed in a structured, machine-readable way. Each triple consists of three parts: a subject, a predicate, and an object. And the subject is the thing being described, the predicate defines the relationship, and the object is the value or the related entity. And together, these triples form a graph data model in which entities are connected through these relationships. The graph structure is what allows RDF to be processed, queried, and integrated across the systems. So, for example, the statement, "This work was written by this author," can be represented as a triple where the work is the subject, written by is the relationship, and the author is the object. In practice, both the subject and the object are identified using a URI or an IRI, which is an international resource identifier, which provides globally unique references to resource. This ensures that the same entity that can be consistently identified. So far we've seen how RDF represents information as triples, forming a graph of connected data. For this model to work across different systems, we need a way to consistently identify the things we are describing. This is where the URI becomes essential. And on the traditional web, URIs are traditionally used to identify and retrieve documents, such as a web page. But the focus is on locating content rather than defining the identity of the thing being described. In the semantic web, URIs are extended to identify not only the documents, but also real world entities. And this means that anything we want to describe in a knowledge graph can be given a unique stable identifier that can be referenced across your systems. Um, the International Resource Identifiers, or IRIs, extends the URIs further by allowing the use of Unicode characters. And this makes it possible to represent identifiers in many languages, including Chinese, Japanese, Korean, Cyrillic, or some other language, Romanized text. Um, Together, URIs and IRIs provide this global identification system that allows RDF to be linked, shared, and integrated. In RDF, each component of a triple has a specific role and meaning. The subject of the triple is typically, again, identified by a URI representing the resource being described. The predicate is also identified by a URI. It defines the type of relationship between the subject and the object. And these predicate URIs are drawn from shared vocabularies, which provide standard terms for describing these relationships within a domain. The object can take two forms. It can be a literal value, such as a string, a number, or a date. Also, it may be another URI representing a related resource. And this flexibility allows RDF to represent both simple descriptive data, but also complex network of interconnected resources. For example, a predicate such as date of birth might link a person to a literal value, while the predicate such as employed by might link one resource to another resource. And together, URIs, literals, and shared vocabularies form the basic components used to construct RDF statements. Okay, up to this point, we've seen how RDF provides a structure for representing data as triples using URIs to identify resources. However, structure alone is not enough. For data to be meaningful across the systems, we also need to share the definitions of what relationships and terms actually mean. And this is where vocabularies and ontologies become important. Vocabularies and ontologies provide standardized sets of terms that defines the type of entities like classes and properties, and the relationships used in this. Because they're shared and machine readable, they allow different data sets to interpret information in consistent ways. Vocabularies are typically used for simpler or more focused sets of terms within a domain, while ontologies are more complex and formal systems that describes richer structures, relationships, and constraints within the domain of knowledge. And by using these shared models, RDF can be integrated across the systems, and machines can begin to perform reasoning and inferencing over these relationships they contain. And this enables more meaningful search, discovery, and analysis of connected data. Together, vocabularies and ontologies also allow data from different systems to speak the same language. So now that we've seen how RDF provides structure, how URIs have provided identity, and how vocabularies and ontologies provide shared meaning, the next question is, how do we actually work with this data? So to do this, we use a query language called Sparkle, which is defined specifically for querying and manipulating data stored in the RDF format. So Sparkle allows us to ask questions over linked data by matching patterns in a graph rather than querying tables or documents. In other words, instead of retrieving rows from a database table, we retrieve connected patterns of triples across the knowledge graph. And this makes it possible to explore relationships between the entities, combine data from multiple sources, and extract meaningful information from interconnected data sets. Sparkle allows us to treat the knowledge graph as something we can actively explore, not just store. Now, this example of Sparkle in action using Wikidata. Wikidata is the largest public knowledge graph of general facts. And there's all types of contributions from the scientific community, from the cultural heritage community, history, the digital humanities have all contributed to it. So you can see there is a hyperlink in the slide. If you go there, you can actually run this query in real time on the query service. So if you go follow that link, hit the blue play button on the lower left-hand pane, you will get the results. So here we're going to ask you a simple question. What research works are related to Arctic and who's authored them, right? So instead of the rows from the table, Sparkle is searching for patterns in the graph. In this case, we're going to match works that are connected to the Arctic topic and then follow the relationships to their authors. So what we get back is not just a list of results, but a network of connected entities. So for example, if I click here, and I'm going to add the graph. So what is it? Default. What is it? Yeah. And I color coded the work. So the works are red, the people are in white, and you can see in the center, the hub, you can see the topic, how these people are connected to the topic Arctic. Let me zoom in here so you guys can see. And then as you click on the entities, you could start further traversing about the people, the works, the topic. So this is live and real-time data being ran. So, okay. The next one. So with this one, we are asking for, let me get a bubble chart of the top 20 authors of scientific articles by their occupation. And that's what we see here. And so this is the data in action. With Wikidata, there's additional services that you could use on top of your data. So if I deleted that top line that I put into the first query, it would just bring you back a table view, which then you could download, save it. Another cool thing about the Wikidata query service is your results can be shared. So I could share the results of the query. So for example, if we want to share these results, where's my chat? Chat. Here, I'll put it in the chat. Oops, that's not what I wanted to give. Copy. Let's try this again. No, why is it not? There we go. So you can run the results there. You can also download it as a series of files. You want it as CSV, JSON, you want XML tables, you could get that. But what's also really cool about the service is you could get your data as like a code snippet in whatever flavor of coding language you're using, and you can embed this in your own website and stuff. This is one cool thing you could do with some of the wiki data and stuff. I often use the OpenStreetMap API to overlay our geographic data that may be in Wikidata or in our triple store, and then we could start mapping out some of the things. Let me see. Let me get back to here, and then let me close this and bring back my remote. There we go. Okay. And then here was another example. Select all scientific journals about Arctic, polar region, and polar exploration. And you can see the results came back with 3 journal titles with 2 ISBNs. I assume one is a print version and the other one is The other ISBN represents the electronic version. But you can see how the Sparkle query in the left-hand pane, very similar to a SQL query, but it's just, it's a pretty similar syntax. We still use the same operators: select, ask, describe, construct. Those are some of the operators and stuff. I also want to show you, let me show you one example. So this is a page that has some different examples. We're able to visualize places within a 50-mile radius around Clark County. So for example, if we do this one and I run it, you can see all the places. We can zoom in using the Street Map API. And these are all restaurants. So basically, I was trying to find where all the restaurants were using linked data and stuff. You could do all types of stuff. Let me see, here goes one with inference. Let me see, the inference one, construct. Oh, data transformation, I also mentioned. So for this one, I'm going to construct a graph of people. No, I'm not going to use that one. I'm going to use this one. I'm actually taking written works out of Wikidata, and I'm actually transforming the data on the fly before it displays it. So I'm basically taking the Wikidata ontology, transforming the result so it will be conform to the Dublin core model. And so this is what this one does. And so you can see in the query, we're using construct. All the previous examples, we were just selecting our data. But now with the data and once you have your triples in your triple store, which is the database for the graph data, um, it doesn't matter what the data is, because you could transform it on the fly when you want to display it, or you can actually transform it before you load it into your triple store. So for example, say somebody has a data set, but you only need a portion of that data set, you could pull it out, transform it, and load it after you transform it. So here goes this query. Oh, it's taking a little while. Yeah, because I'm constructing. All right, here we go. And so you can see here goes the triples. So you have the identifier under the subject. You have a RDF type. So the RDF type tells you what class the entity is. That's the first thing you do when you create a new entity in a triple store. You define what kind of class it is. It's a person. It's a bibliographic resource. Uh, it's a subject heading. You would type it. It's a corporation. And so you see these triples. And so you can see my results here and what I'm dealing with. So I'm dealing with books. I'm dealing with the subject. So the linguistic system is dealing with the subject. And you can see we're having these titles and all these properties. So that's actually what the data in a triple store would look like. Like I said, it's a 3-column table basically. And then we just uniquely we reference the entity one time. And so like a table, there might be if you had a table that was called people, and then you had a column that was first name, there might be hundreds of Johns in there and they're all different, right? But in a triple store, we could add John, type it as a first name or a given name, and then we could reference John across different entities. And so you get the deduplication of records, your data is more concise. You don't have that conflation of similar things or the same things in multiple records. And this is where the real power is. It makes searching the database really more powerful. You can index the whole thing. I won't talk about it today. There's also a thing called quad stores. So the RDF deals with triples, but we also, if you see here, there's a fourth column called context. And that's for if we were dealing with named graphs. So if you wanted to subset out your data, like, oh, all the names will be under its own context. All the subject headings would be under its own context. And so you could then further type that. And that gets really helpful, especially if your data sets are like super long. So on that note, that is the end of my presentation, and I'm more than happy to answer any questions for you guys, or if you want to see some more examples, I'm more happy to talk about that as well. But yeah.
How do you want to handle questions?
This is great.
Thank you.
I was trying to take tons of notes here.
Yeah, and I'll make the slides available. So if you guys will want these slides and some of those, the links to some of those examples and stuff, you're more than welcome. I'm more than welcome to share it with you all.
Amos, to answer your question, I think if it sounds like you may have a question, but I think using the raise hand feature, if folks are able to do that, is great. Or just put a note in the chat either with your question or, hey, I'd like to jump in.
Yeah.
And Darnell, I think you can pull down the screen share and then we'll be able to see folks.
Okay.
Yeah.
Yes.
Darnell, thank you so much for that. That was great. I have, we're getting into sort of practical implementation stuff right now with our group, and I have a fairly, a deep technical database and computer system background, but the graph database stuff, although I understand the concepts and we've been doing stuff similar in some of the software frameworks we've been building over the years, with linked documents and these sorts of things. But when I start to look into graph databases now, and particularly when we're trying to deal with stuff where we're trying to do it being sensitive to sort of data sovereignty issues and that sort of thing, we're trying to do this locally on our own systems with databases. We're looking at open source solutions, and we want to make sure that we're building something that's not going to be a burden for anyone in the future. So there seem to be a number of different graph databases, and some of the most popular ones are, commercial endeavors. I'm thinking about things like Neo4j and that sort of thing, and then some of the stuff that's showing up in the cloud. But on the open source side, there seems like we've looked at a few different things, and they seem to sort of come up, go for a while, maybe run into some difficulties. Maybe the team moves on to other things or whatever. Yeah. Have you got like, I don't have an extensive list, but we're exploring Age right now, which Apache Age, because we do have a lot going on with Postgres and PostGIS and other types of things going on in PostgreSQL. So that would be helpful if we could reuse some of the same technology from just a sustainability and maintenance point of view on our end. That project seems to be went through a little bit of a lull, and seems to like there's some people continuing it and picking it up again. I'm wondering if you have any other thoughts on things to use. I see now there's also, like I just discovered the other day, something called Tinkerpop. It's Apache Tinkerpop. I don't know how familiar you are with all the different landscape.
I'm not. Well, yeah. For my experience with the open source, what's been critical was Apache Jenna, was the triple store. I've used it in the past. I know that it's compared because there's been benchmark studies on triple stores, and it doesn't scale as well with the large graphs and stuff. Wikidata, which I just gave an example, is the largest public knowledge graph out there, and that is using BlazeGraph as their backend. Over the past 2 years, we've split the graph, so now there is a separate scholarly graph because again, we're talking over trillions of triples,
Hmm.
so the scaling at that point has gotten better. So basically what they've done is, like I mentioned, the fourth column where you start getting in the name graph, you'll start subsetting your graph. Once you get past of a billion triples, you might want to start thinking a little differently about, and that's normal, like with, spreading your data across different servers, balance the loads and stuff like that. But that's standard database. You're going to be doing that when you're dealing with databases and large data enterprise databases anyway. So
Hmm.
I
Hmm.
personally use let me pull it up. Oh, I'm not sharing anymore. I use GraphDB. I found really good success with it. It was very easy to spin it up. Um, you just configure your ontologies. You load your ontology files first, and then you add your namespace declarations. You have like a control list of all your namespace declarations, so you could use like shorthand in your in the coding itself, and then you just start loading the file and your files and stuff. And you can either load it in as a bulk load, or you could load it like incrementally, or if I'm working on a record, um and I'm doing it one at a time, or because I do a lot of, in my workflow, I have a lot of authority. I'm an authorities creator too, so I create NACO authorities that are a part of the Library of Congress name authority file. So I have to do that work and then incorporate those URIs from the name authority file into our local RDF files to make that interoperable. Because it's one thing to have the data, but what makes it powerful is when you take your data and start linking it to other things, because that's when the serendipitous discovery starts happening, and these new relationships will emerge, stuff that you're not even looking at. It'll just naturally emerge, It was like with me, one of the biggest things was working with creating authority records with civic organizations, and then seeing how people were members of this organization. And then you started to see how these hubs started emerging on the graph, where all these lines started connecting to these things. These hubs will start appearing and stuff. And then that really gives you insight. As far as sometimes you might have a disjointed node, and it might, you look at it on the graph and it's this thing floating, an entity's floating, but it's not connected to anything. That's a sign of a data quality thing right there. Your relationships aren't there, or maybe you forgot to add that ontology in there. There's a record using a certain ontology, but the ontology file isn't in the database yet. So you could use the graph actually
Yeah.
as a data quality tool as well too.
Or somebody needs to invite that entity to the next meetup or something because they're not connected. Yeah, which we see too, right? And you're dealing with groups, and it's like, oh, these guys are off doing their own thing, and they haven't got very many connections or whatever. Yeah. Okay. Thanks.
Yeah. Yeah, I wrote a Sparkle query once. I was trying to find all faculty people who may have similar research areas that may be spread out in different colleges and stuff. And I created a graph that looked at my university faculty. It's actually pretty cool. Let me see if I can share it with you guys. Go back to our data queries. So I'll go ahead and put it in the yeah, there's actually two. Actually, you don't mind, I'm gonna share my screen one more time. Uh, so all these queries can be found here on my Wikidata documentation page. Yep. And Lauren, yes, GraphDB on text. Yep, that's the company. So, but yeah, so for the first one, this is actually so you harvesting all the location data from our records and our in my special collections. I'm actually going to use the OpenStreetMap API to give you a visual representation of what locations our collections are about. And using the GeoNames ontology and the GeoNames database, we were able to now do this. And so you can see we start zooming in. Our collection strength is on Southern Nevada, but our collections are international in scope as well. And like I was saying, the serendipitous discovery that happens. So one time I was giving this talk using this exact query, and I started zooming in to the level of where you can start seeing the highways, and you start noticing that the migration patterns all correspond along the highway system and stuff. Never even noticed that before until I just zoomed in at that view. And that's where that, like I said, these connections might start emerging that you had no idea they were there, you know. So, Manish, you got a question? And
Maps
Hazel
are fun
and
then.
John. Yep.
Yeah, my question is about GraphDB. We tried using it on a project last year, and we ran into limitations with the free version with concurrent queries. So it didn't actually work out for us. I just wanted to know if you were able to get around that, or if you have any recommendations for free alternatives.
Now, what do you mean by concurrent queries? Like,
We found that when we had the free GraphDB installed, we
mm,
could only do 2 queries at once. Otherwise, the performance, it just wouldn't work. And that was the limitation with the free version of GraphDB.
hmm,
Paid versions that take that away,
oh,
but we don't.
yeah, I'm not too sure. But I also sometimes notice that the way you write your Sparkle query would impact performance and stuff. So you may want to look back at the way you wrote your Sparkle query. And there might be another way to actually get your performance level, because I've done that before where I've had to rewrite queries and think about it in a slightly different way to get the performance, your performance right.
Okay.
As far as that, I've never really ran simultaneous stuff unless I'm doing like a nested subquery, like a query and a subquery. Like I might be um, doing a federate search where I might be pulling data, say, out of Wikidata, and then also pulling data out of, DBpedia, and then putting it all together on the fly and stuff. Um,
Okay,
no,
yeah, like our use case was doing it for search engines, so we had multiple people using it at once.
got you. Okay, now that makes more sense and stuff. You might need to. I don't know how you had it set up. Did you have it set up on one server, or did you
Yeah,
have it
yeah,
distributed?
it was all set up on one server.
Yeah, you might need to distribute once you start getting into, large graphs and stuff like that with, multiple simultaneous users, you might really have to think about your strategy and decentralize this stuff. So like normally, like how we have it set up, we basically have like our production server, and then we have like a sandbox on another server, and then we might have backup on another server, and then by,
Okay.
distributing it like that, it greatly improves performance.
Okay, thanks.
Yep.
Hey, Manish, that was CCADdy stuff.
Yeah.
Yeah, we should chat about that sometime.
Yeah, we ended up switching it over to Postgres. It's actually working pretty good now, but yeah, we can
Yeah,
chat about
okay.
it.
Yeah, I think that. Okay.
Thanks for the talk, Darnell. My question was about, I guess, like building these databases. So I can see that this would work. Like I'm picturing, okay, you have a library of a lot of publications. The authors have ORCID IDs, so you know how to link those like people to a persistent identifier. The publications have DOIs, the data sets maybe have DOIs, and you could build a really interesting graph database, I think maybe somewhat easily out of those pieces. The work that I do is largely focused on Arctic observing systems, and those can be kind of invisible in those data structures because sometimes it's clear like how a data set is built, but it's not always like that easy to figure that out. And so we're working on building out some of those capacities to better kind of like do the foundational mapping of the observing system. But I guess I'm curious, yeah, if you have any thoughts about that or kind of how these get built.
Yeah, so that's in the phase of the data modeling, when you start deciding, well, I'm gonna use these ontologies, these vocabularies. I may need to create my own ontology or, use the whole idea with linked data. You want to reuse, like most people, most people know Dublin Core without even knowing Dublin Core. Like if you've ever filled out a database that said date, title, author, contributor, those things that you're using Dublin Core properties and or classes. That's where you start. It's like you're drawing your map. You want to define what classes you're going to be using. You want to define and basically what you would create is a metadata application profile, and that will first list all your classes. And in the classes, you will have the constraints. You will then, each class will have a set of properties or relationships. And then you could start checking on that and doing your data validation. And I would approach it as an iterative process because you're going to design, you're going to test, you might need to tweak, you might want community feedback, and then you're going to iterate over it until you get the right model and stuff. Sometimes these large models could take years, sometimes you could do it really quick, but there's actually a lot of ontologies out there to use and stuff. If you go to, what is it, LOD/cloud.net. Let me see if that's the right URL. LOD/cloud.net. And put it in the chat. So that is actually the linked open data cloud. So this is all the published data. So there's linked open data and then there's linked enterprise data. This is the linked open data cloud right here, and you can see it's pretty robust these days. It started out in 2007 and there was only like maybe 8 data sets, all centered around DBpedia and GeoNames. I didn't see. We can keep rolling questions.
The recording's coming for anyone that has to hop off like a few minutes early.
Yeah. So, any other questions? I think Rosemary has a question.
Yeah, this is Rosemary Atongarok. I live in Norksett. One of the questions I have is there are efforts to create layers of information and various time boxes of information, but there's ways that presenters can create blockage of information by exclusion. Like we were trying to look at some overall information related to air quality. And because the contractor was one company, they wouldn't include a recent event in the data information and stop the querying of data in our station. And so trying to look at ways that others are trying to approve projects and are creating layers of information, but that makes us who are working really hard to create the protections we know that need to be created have to find the gaps in what's being presented to show that we're missing layers, especially now, that are critical in these decision-making criteria that are non-existent?
Yeah, no, that's been a common thing. That's nothing new in this information landscape. Available information disappearing, or once freely available information is moved behind firewalls or paywalls and stuff like that. This is why I'm such a proponent of linked open data, and that's where if we have open rights, the data will flow. But then there's also those ethical things as well, as far as the privacy and the protections that you would need to build in and stuff. And so there is there are ontologies out there for preservation, for privacy restrictions and stuff like that. We just actually, in our graph, which is primarily cultural heritage, it's a knowledge graph consisting of cultural heritage triples. We have restricted data as an archive. We have restricted data that may be restricted indefinitely. We may have stuff that's partially restricted for a time being and stuff. And so we have the mechanism we just implemented where our system actually manages restrictions. So before that, I would have to get a notification. All right, this date came. Let's unrestrict this data. Now the system is doing it automatically. You just built it in and stuff like that. But really, the key is try to use as much open information as possible, is because you'll have these problems. And I've seen this before. A perfect example, what was it? Freebase was an open source community. It was the first knowledge graph, and that's what became the Google Knowledge Graph. Google bought Freebase, and then they incorporated it into their knowledge graph and then added on to it. But yet that was an open source project, primarily volunteers. And then now Google has monetized. I mean, you can see this goes back to the Disney stuff. This is the classic Disney story. Yeah, I mean, they've taken open public domain stuff, the Brother Grimm novels, and then they've basically have retold the same stories, and now they got patents and stuff. They've patented stuff that was public information. And so as a data security thing, that's one thing you might want to keep in mind. As we use these web technologies, we're in a world now where corporate law overwrites our constitutional law. When you go to a web application or a website, first thing you do is, do you accept these terms of use? And most people click agree before they don't even read it. And then you got companies like Google. Google issues an update to their terms of use policy every Wednesday. Yeah, I mean, I don't even think anyone's ever really read the Google public use policy. So, what people can do with your data, what people that you really have to think about that, not as an afterthought, but during the design, as when you're designing your systems and stuff.
I think this is really important with the different layers of data that's on the eastern side of the Arctic versus the western side of the Arctic, in insinuations for project development because of the concentrations that can be found on one side versus the other. But when you start doing modeling that goes across this great distance, the concentration of the numbers are not the same, but the modeling can be incorporated to show that it's going to be okay because we have numbers in different areas. So thank you very much for sharing information and helping me understand a little bit better. I'll go back and look more at the video once it comes out, because I couldn't get started in the beginning, but this is very helpful in some of the blockages that I'm having in trying to look at information. Our biggest obstacle is we don't have control of the way that research is being done, but we have to respond to the research that is being done with our traditional knowledge, and don't have the data sets to support our traditional knowledge.
Yeah, and that's a big thing. That's the one reason why I love graph databases so much, because oftentimes the information is out there. It might be sitting on one of your colleagues' desks, or in one of their homegrown local databases, or, and then when you get to a point where somebody retires, may leave the organization, you know, the information really becomes siloed and stuff. Because often, you leave an organization, you don't have access to that, that account, that acute computer. And so I've seen where important data has become orphaned just by that, so yeah, something to very keep in mind as you work through your data management strategies.
I think we have another question in there, or a hand raised.
Hi, I'm Juliet. Great presentation. Lots of great other questions too. The kind of few thoughts. I'm trying to pick one to start with. And having worked a lot with creating metadata schemas using XML, traditional things, how easy is it to like kind of port that over to the GraphDB structure? Are there other layers to that to be thinking of in terms of GraphDB compared to thinking about an XML structure or a JSON, GeoJSON type structure?
Yeah, so all this stuff really ports on the metadata. So in cultural heritage, we have a lot of that work has been done before by the Library of Congress, the PCC. So for those of you who don't know, the Program for Cooperative Cataloging is a program of the Library of Congress. And so the PCC members are those who are contributing. So they're under the PCC, there are a couple different organizations. There's the NACO, the Name Authority Cooperative Organization. There's the SACO, the Subject Authority Cooperative Organization. Then you have Consor, which deals with reoccurring materials like periodicals and stuff and title forms like that. So I'm a NACO cataloger. So I can contribute to, or edit the Library of Congress Name Authority file. Some of my colleagues work in SACO funnels, which you'll be able to contribute or edit the Library of Congress subject headings, which a lot of the subject headings come from. You have FAST, which is a vocabulary that's a subset of the Library of Congress subject heading. And then you have all these other types of vocabularies, like the Getty Institute has a bunch of them. They created the art and architecture thesaurus, which is an ontology and vocabulary for artistic works, artistic forms. You have ULAN, which is a name authority file of artistic names. So you have all these authority files in play. And so working together. So if you're describing published works, you could use the Library of Congress authority records in your graph database. They have all different serializations. If you go to id.loc.gov, that is their linked data service. They have APIs there, and then they also have their RDF data set. So all the Library of Congress authority records are now published in RDF form. So you could load those records from Library of Congress into your triple store and use those as your authority control.
That gets to kind of my stacking questions. So I tried to do a search for data we published before to see if people were using the DOI, because I thought I could make a big web network graph, right, of who was using what and see how it branched out. Like nobody was using the DOI, so it didn't go very far. But are there ways to like I guess I would like to try to tease at that idea more, and figure out how to get the DOI, see who's using it in a different way. It seems like these resources might be a little bit better. I worked with the librarians at UNH to try and figure out a little bit about what databases to be pointing to, because some resources were showing the geospatial data, and like the journal archives was like only a few things.
Right. It's going to be a hodgepodge thing. So, you would come up with your strategy. As far as the DOIs are concerned, you could do the best way to find the impact is start doing citation tracing, so you got to go to the journal articles and trace the DUIs that way. Google Scholar is a really good tool, but there's also another one called Semantic Scholar. And it's basically like a graph version of that, but you're going to have to look in different places because, you might have to look in Scopus. You might have to look in was it the ARIV
Oh,
repository,
Arvix.
Arvis. You might have to look through Arvis and pull data from there. You might
I'm blanking right now, but I did several of the librarian suggestion, and some were very good, and some were like, yeah, they only had like the journals that like paid, as I said, the ones that paid money. Google tended to be a little bit broader, but it still was not picking up a lot of the geospatial.
Yep.
Not things that did not go through a traditional publishing clearinghouse. So like it was, there was a great mix of things. So
Right.
it was, yeah.
No, and the data, and so curating that data, there's always still going to be some reconciliation and stuff. Because even with the DO, if you notice when you go to those databases, the DOIs aren't even the full resolve. Sometimes it just might be 10 point something, and one database might have https doi.org/10, something, So that data consistency thing is always something that's in my mind, thinking about, okay, I may have to reconcile data um, to normalize my data. But I think regardless of whether you're using relational databases, no relational databases, or graph databases, that data cleaning aspect of it is always going to be a part of it, especially when you're integrating your data from all types of different sources and stuff.
There's been a lot of excitement about this topic. We're now 10 minutes over. So and I don't want to keep everybody too long, even though I didn't get to any of my questions. So I'm gonna have to like
Hey, I got time. I mean, right now I'm just about to go to lunch and watch a World Cup game, but if you, like I said, you guys got my time. I blocked off the whole morning for you guys. So if you got to cut it, that's fine. If not, I mean, I got until about 11:30.